Alright, so we saw very quickly at the end of the last video that we have these two eigenvalues for A, and we figured out the eigenvector corresponding to this one, which I'll call maybe V2, was the vector 1, 1. Or I shouldn't say the eigenvalue or eigenvector. There are always infinitely many eigenvectors that work. This is just a simple one that we can choose. And I asked you to check those details. Just go ahead and solve that system of equations and make sure that that's what you got. Now I want to work out the one for lambda 1, which is negative 1. So if we do this, we are trying to find the eigenvector associated with it. Also, the reason why I called this one V2 is because it was associated to what I called lambda 2. That's the only reason I called it V2. So if I try to solve for a minus lambda 1 times the identity multiplied by v set equal to 0, this is the same thing as saying a plus the identity. Since lambda 1 is negative 1, that's going to turn that into negative 1, which is going to become plus. Alright, so I'm going to have a plus the identity times a vector, which I'll call ab, should be equal to the 0 vector. And a plus the identity, right? This is a, so a plus the identity is going to be 2, 2, 2, 2. Right, so this is going to be 2, 2, 2, 2. Multiplied by AB should be equal to 0, 0. And what does this give me? I've got 2a plus 2b should be 0. And the exact same thing in the second component. So a should be negative b would work, or b is negative a, whatever you want to say. However you want to say this, v1, right, my first eigenvector, I'll just take b to be 1, which would make a negative 1. Right, this works. Okay, so what this gives me is two eigenvectors we've got v1 is negative 1, 1, and v2 is 1, 1. Right, so these are my eigenvectors for A. And pause the video for a second after I give you this prompt and think about what is significant about v1 and v2 here. This is a very open-ended question, of course, but what is significant about v1 and v2 here? What can be said about the collection v1, v2? All right, so take a few minutes, try and think about what can be said about v1 and v2 together. All right, so hopefully you thought about this for a little bit, and you either have no idea what's happening here, but you struggled for a little while, or you thought about it and you came up with something. There are many things, of course, that can be said about v1 and v2 here. The simplest thing that can be said about them is that v1 and v2 are actually linearly independent. It's not too hard to see that they're linearly independent. If you draw a picture of them, you can very clearly see that they have to be linearly independent. Right, there's v2 and v1 looks like that. They don't point in the same direction, which means for two-dimensional vectors that they must be linearly independent. All right, and this means that the collection v1, v2 is a basis for R2. All right, anytime you've got two linearly independent vectors in a two-dimensional vector space, in this case R2 is two-dimensional, we know that, they have to form a basis. So, isn't that interesting? we've got a matrix, and this matrix has two eigenvectors, and they are linearly independent, and that means that they form a basis for R2. Now, there is something even stronger that you can say about these, right? These two particular vectors. Not only are they linearly independent, they are the most linearly independent that it is possible to be. They are actually orthogonal. V1 is actually orthogonal to V2. If you dot them to check this, you get 1, well, technically you get -1 plus 1, which is 0. So these things are orthogonal. Right, so they are at the most linearly independent that two vectors can possibly be. And this is interesting. All right, let me tell you why this is interesting. And again, I'm giving you the super short version of this, but let's see why this is interesting. All right, the fact that these two eigenvectors form a basis for R2, this has serious consequences. Right, this means, what does it mean to be a basis? This means that any, let's say U in R2, right? Any two-dimensional vector in R2, any U in R2 can be written uniquely as a linear combination of these basis vectors. As a linear combo of the basis vectors, which are the eigenvectors v1 and v2. All right, so let's give the coordinates the names C1 and C2. And now what we can do is, let's say we want to know what A does to any old vector U, right? Any vector in R2, we want to know what A is going to do to it. We know very, very, very specifically what A is going to do to V1 and V2, because those are extremely special vectors. Those are the eigenvectors. But not every vector is an eigenvector for this thing. So what is it going to do to anything, right? So AU, well, this is going to be A applied to C1 V1 plus C2 V2, just using the basis expansion. And now we can use the fact that A is linear, meaning we can distribute A through this sum, and we can factor out those constants. We get this. And now we can use the fact that AV1, or that rather that V1 is an eigenvector corresponding to lambda 1. Oops, not A. V1. And here, this is lambda 2 V2. All right, so here we're just using the fact that these are eigenvectors, right? The basis happens to consist of eigenvectors of A. So this is going to look like C1 lambda 1 V1 plus C2 lambda 2 V2. And we know exactly what lambda 1 and lambda 2 are for this very specific matrix, right? We know lambda 1 is -1, lambda 2 is 3. We know V1 is -1, 1, and V2 is 1, 1. Right, so we actually know a lot about this. But here's the really important thing that I want you to see. What knowing the eigenvalues and eigenvectors of A really tells you is that you can take A acting on absolutely any vector in the space, and you can figure out what it does in terms of its eigenvalues and eigenvectors. All right, so it's possible to rewrite how A is going to act on some vector, how it's going to change it, by writing out exactly what it's going to do in terms of its eigenvalues and eigenvectors. All right, so this is monumental in the history of math. This is absolutely enormous. this discovery, and for so many reasons. Again, this is the super, super short version, so I don't really have time to get into all of it. However, let me just say this one thing as to why they're called what they're called. Eigen, the prefix on eigenvector and eigenvalue. Eigen is German, and it means, it has a lot of different possible translations. It means own or self, and the most commonly translated version is characteristic. All right, so the reason why the Germans, who originally formulated all this theory, the reason why they called them eigenvalues and eigenvectors is because they are characteristic vectors and characteristic values for the matrix. Characteristic in the sense that you can take your matrix applied to any vector in the space, and you can decompose it into a statement purely about its eigenvalues and eigenvectors. All right, so that's what they mean when they say these are characteristic values. They completely determine the characteristics of your matrix. All right, so this is wild. I can show you just a quick example of what I mean by all of this this stuff written on the page here, in terms of that matrix that we just worked with a second ago. All right, so if A is 1, 2, 2, 1, we know, right, we've done the legwork. We know that lambda 1 is -1. We know lambda 2 is 3. That's a terrible 3, but forgive me. We know that V1 is -1, 1. V2, and again, these were the choices that we made for V1 and V2. You don't have to make these same choices. There are infinitely many valid choices for V1 and V2, as long as they're not 0. And we did an example in the last video where we looked at what A did to the vector 1, 0. All right, and we found it was sent to the vector 1, 2. All right, so let's work with this a little bit now. So 1, 2, I'm sorry, not 1, 2, 1, 0 has some expansion, right? It's got some coefficients in the basis V1, V2. And even more than that, we know that because V1 and V2 is not only a basis, but it's actually an orthogonal basis, we know exactly how to calculate C1 and V1. Right? So in particular, if we were to dot both sides by V1, well, that's going to give me C1 V1 dot V1 plus C2 V2 dot V1. This is stuff I went over in the basis theory videos. V2 dot V1 is 0 because they're orthogonal. And so I'm left with V1 dot 1, 0 divided by V1 dot V1 should be C1. All right, so C1 should be V1 dot 1, 0, and V1 is -1, 1 dot 1, 0 over V1 dot V1, which is going to be 2. All right, so this thing is -1 over 2. That's C1. All right, C2 very similarly is 1, 1 dotted with 1, 0. Right, so that's V2 dotted with 1, 0, divided by V2 dotted with V2, which is 2, and so we get 1/2 for that one. And again, I'm being a little more formal and detailed than I really need to be here, but what we find is that 1, 0 is equal to -1/2, -1, 1, plus 1/2, 1, 1. Okay? Now, the idea behind all of this stuff that I was just saying a second ago is that now we can figure out a of 1, 0 fairly quickly. This is going to be negative 1/2 times a of negative 1, 1 plus 1/2 a of 1, 1. And a of negative 1, 1, well, this is lambda 1, which is negative 1, times negative 1, 1, plus 1/2 times 3, which is lambda 2, times 1, 1. Alrighty, so this is, so many negatives. Negative is positive, negative is negative. So that's negative 1/2, and then positive 1/2, plus 3/2, 3/2. So this turns out to be 1, 2. Now, you might be thinking to yourself, why is he doing this to us? We could have just used the original matrix to say exactly what the output was going to be here. Right? We could have used the original matrix, multiplied it by 1, 0, and saved all of this time. We wouldn't have had to do any of this. And yes, I'll grant you that is true. However, this is why they are called characteristic values and characteristic vectors. Because if we had known only that the eigenvalues and vectors of this matrix were what we know them to be, right? So lambda 1 is negative 1, lambda 2 is 3, v1 is negative 1, 1, v2 is 1, 1. Right? If we only had that information and not the actual matrix in front of us, we still could have calculated what this matrix, this unknown invisible matrix to us, what it did to this vector, only knowing its eigenvalues and its eigenvectors. This is really the crucial thing that I want you to see here. This is why they are called characteristic values of a matrix. It enables you to do all of the matrix calculations without having the actual matrix in front of you. You just need to know this amount of information about it. Okay? So this is why this is an important thing to know how to do and an important thing to be able to work with. Let me briefly go through the example that I gave first of why this is a non-trivial problem with this 90-degree counterclockwise rotation matrix. Let's use the methods that I mentioned. So first we'll calculate the characteristic equation. This is the determinant of a minus lambda I set equal to 0. That's going to be the determinant of minus lambda minus 1, 1 minus lambda set equal to 0. This is lambda squared minus minus, so plus 1 equals 0. And now if you try to solve this thing, you have to take the square root of negative 1. That gives you eigenvalues of plus or minus I. Right? So plus or minus the imaginary unit. That's bad news as far as real numbers are concerned. Remember earlier I said this thing has no real eigenvalues. Well, it turns out that it does have eigenvalues still. That is a result from abstract algebra. It does still have eigenvalues. However, they could be complex. In this case, they could be imaginary. Okay, so the fact that it has imaginary eigenvalues means that it also has eigenvectors, but those eigenvectors are going to be complex or imaginary. So that's bad news as far as real values are concerned. However, I wanted to just show you that this calculation still does sort of validate what I said about this matrix originally, just from looking at it visually. Okay. So the next thing I want to do is just make a couple notes about this example that we did here. Here we got lambda 1 and lambda 2. They happen to be real values. We got v1 and v2 that happened to be orthogonal to one another. This does not have to be the case, okay? So the eigenvalues and eigenvectors do not need to be real numbers for the eigenvalues, and the eigenvectors don't always have to be orthogonal, mutually orthogonal to each other. This is a extremely special case of finding eigenvalues and eigenvectors, and it is because of the structure. Where's my matrix? It is because of the structure of this matrix. All right, it's an extremely special matrix in terms of how it's shaped and the numbers that go into it. So that's what I really want to build up to here. That's what I really want to talk about. What we just saw with 1, 2, 2, 1, this was a very special case. It had real eigenvalues and it had orthogonal, mutually orthogonal eigenvectors. And this is uncommon. This is not something you see every day. Let me give you one example of eigenvectors that where the eigenvectors don't behave as nicely. Okay, let me give you one example of that. All right, let's consider say 0, 1, 0, 0. All right, let's make this our matrix. And if we check the characteristic equation, we will get the determinant of minus lambda, 1, 0. Well, that was odd. Minus lambda, set equal to 0. And what we end up with here is lambda squared equals 0 is our entire characteristic equation. And so we only have one eigenvalue, which is 0. Right, there's only one eigenvalue for this thing, and it is 0 itself. So if we look at a minus 0 times the identity, v equals 0, this is telling us that a times some vector ab should be equal to the 0 vector. Here I'm just checking to calculate the eigenvectors. And so this says that 0, 1, 0, 0 times ab should be 0, 0. And so what this gives us is that 0a plus b should be 0, and this is a very degenerate linear system. That's all it comes down to. Right, it just falls apart into that one equation. And so the n eigenvector corresponding to this thing would be 1, 0. So we get a single eigenvalue, a single eigenvector, and all the things that I was saying about the last matrix, where I was saying, like, okay, we get this really special case where we have two eigenvectors, and not only are they linearly independent, but they're actually orthogonal to one another. Here, you can't even discuss that, because you only have one. You only have one eigenvector, and it's 1, 0. So everything I was saying before is, well, it's not going to apply. Let me put it that way. So the fact that we ended up getting all this really nice stuff for that matrix 1, 2, 2, 1, again, was because of the very nice structure of that matrix. Okay? So I want to talk about those matrices in particular, their structure, why that structure is nice, why it gives us all these nice results. All of this other stuff is really better suited for a linear algebra course. We simply don't have time to touch upon why all this stuff is important, why it's useful, how to make sense of it, etc. All right, so we'll stick to the case where we have a very nice structure for our matrix. All right, so in particular, what was the very nice part of our matrix A, which was, right, the example I gave was 1, 2, 2, 1. Well, if you look at this thing, what's very nice about this is the fact that it is symmetric. Symmetry in a matrix means that its transpose is equal to itself. All right, and to transpose things, remember that you just switch them across the main diagonal. All right, so I can give you an example. If I look at the matrix 1, 3, 2, 0, 0, 1, negative 1, 2, 1, right, just making up a random matrix here. If I were to transpose this thing, I keep the main diagonal the same, and I flip everything across the main diagonal. All right, so this would become a 3, gets switched with that 0. This 2 in the top right corner becomes a negative 1, and then the 2 and the 1 switch. All right, so this is how you take the transpose of matrices. And the thing to notice about this A that was really nice before was that its transpose is itself. Okay, so this is very nice for a number of reasons. Let me state this as a theorem. If A is symmetric, then all of its eigenvalues are real. And here's really the pinnacle of why these matrices are fantastic. Not only are all the eigenvalues real, but the eigenvectors form an orthonormal, or I'm sorry, let's just say orthogonal, form an orthogonal set. Okay, so this is the idea. We are going to prove this stuff a little bit later. All right, but this is the big idea. This is why symmetric matrices are so incredibly nice. They have the best possible situation for their characteristic values and their characteristic vectors. Their characteristic values are all real, and the vectors are the nicest possible set of vectors you could ever have, or maybe one step away from being the nicest ever. They're orthogonal, and if you want them to be the nicest ever, of course, you can unitize all the vectors to make it an orthonormal set. All right, so this is like the best case scenario you could ever really hope for. So we'll talk more about this in the next video.